We have been using the type of function to check what type of data is in our vector, and that's very useful, especially when I'm at the console and I want to directly see what type of data a vector contains. However, sometimes it's useful to know what type of data a vector contains within our scripts. And an output like character or integer may not be as useful as a logical. So it's good to know about the is functions. The is functions allow us to see if there is a certain type of data in the vector. For example, let's ask if even nums is an integer. Now, to remind you, even nums contains 2, 4, 6, 8, 10, 12, 14, 16. So let's ask if it's an integer. And the answer it gives us is false, because remember, even nums was actually double. These numbers don't have the L after them to indicate that they can only be used as integers. They could be used as real numbers. So we could think of the 2 as a 2.00000. If we ask if even nums is double, as I do here on line 128, that's a true. How about even nums 2? You might remember that even nums 2, you can see it down here in our environment, did contain those L's when we created it. And so even though it looks just like even nums, we know that behind the scenes, we created an integer. And so if I ask if it's an integer, I get a true. You notice that those two vectors look just alike when I type them in my console. And so I might wonder, why is one working in a function and not the other? Using the is can help me distinguish that I have integers in one of those vectors and doubles in the other. Watch what happens when we ask whether the vector is numeric. So, is numeric even nums? Yes. Is numeric even nums 2? Yes. Remember that integers and doubles are both considered numeric. Here's a couple more useful is statements. Is logical? True or false? Is illogical? We created true or false as a vector that was logical. Our course, a reminder of what that looks like. Our course are these letters. Is that a character? Yes, it is. Now here's an interesting one. Is atomic? Now you've been seeing that all our vectors up to this point are atomic in nature. In fact, if we try to put in different data, it coerces it to atomic. So you might wonder, why do I need to ask if it's atomic? As you'll see, there are different data structures other than vectors that don't have to be atomic. So it might be helpful to see if those data structures all contain the same type of data. And so that's where is atomic can come in handy. Of course, for our vectors, they are all atomic, and so it gives us a true. And we can even ask, is it a vector? And we find true. But, as you might suppose, we can use is a vector for things other than vectors, in which it would tell us false. There are a few other useful vector functions. Let's look at them. We've seen that function calls are of the form function name stuff, where we send the function something in parentheses. Here I have stuff in parentheses. As we're going to discuss in more detail later when we talk more specifically about functions, the stuff is called an argument. I've mentioned that. Let's look at a few more useful vector functions in which we send vectors as an argument. So that's what makes them vector functions. We're looking at a function in which we send vector as an argument. So here's one that's going to be called as numeric. So remember what our true or false had. True, true, false, true, false. This is logical. But I'm now going to create a vector that I am naming. This is a name I'm giving here on the left side, logic to numeric. And the function I'm using is as numeric. Sorry, I've named that function wrong. Just a moment. The functions are named with periods separating the words, which is why I actually use underscores to separate the words to distinguish my objects that I create from the periods that are in the base R, but I confused myself there. I wrote the function with the underscore, but the function should have a period. So let's try that again. Logic to numeric. So we're using as numeric. Now let's look at my logic to numeric vector. Notice that all the trues were set to 1 and all the falses were set to 0. Let's take even nums. Again, that's this one that has doubles in it. Let's take even nums and use as character for even nums. You can probably guess what's going to happen here. I called that function numeric to character, and all it did is put quotes around them, and so now it's a character. Here's one more that's important to know about. I'm going to take even nums. Again, even nums are these doubles, and I'm going to switch them to logicals. What happens then? Let's look. Numeric to logical. They're all true. Now, true is indeed a logical, but why numeric to logical? Why did it switch them to all true? Here's the rule. Anything that's not 0 is true. Anything that's 0 is false. So when we look at any number, whether it's an integer or whether it's a double, any number, if we switch it to logical and it's not 0, it's going to be true. So look at what would happen if I used the as logical function, but now used it on 0. Now I get a false, but that's the only time that I'll get a false is when it's a 0. Here's a useful function for finding out how long a vector is. That is, how many elements does it contain? That's the function length. And it tells us that even numbers has 8 elements in it. 8 numbers. If I look down here in the environment window for even numbers, you can see it's 1 through 8. So that was easy to see in the environment window, but imagine if you had had 1,262 elements, then that length function could come very much in handy rather than you counting by hand. A scalar is just a vector of length 1. So let me set the number 5 to my scalar. So I now have my scalar, and it's the number 5. If I look at the length of my scalar, it's a vector of length 1. If I look at the length of 5, it's a vector of length 1. And in fact, you notice how you have a 1 in your console window every time we print out one of these vectors? That's basically telling you the first element that you see is the first element. If you had a long vector, then the next row would say something other than 1 to tell you what was that element you were looking at on the next row. So even when we use these numerals like 2, 2 is a vector. It's a vector of length 1, which has a special name. We call that a scalar. We indicate that an element of a vector is missing, so missing data, that's going to be useful in research, we indicate it with the capital NA. So notice the vector I'm creating right here called my data. My data will be created just fine, but notice when I print it out here that my data has an NA, and notice that it's not in quotes. That would defy the atomic vector principle, because that would be a character in the midst of these other doubles, and you can't have that. The NA is not in quotes. It is a special symbol to indicate that there's missing data at that point. We can use is NA, which notice I've already done it again. I'm catching myself ahead of time. I put the underscore there. Is NA is the function for my data, and when I run that, is NA for my data. So what it's doing is it's talking about is NA for each point in the data set. So here's the first value, 59, is not missing. That 59 is not missing. But over here in the 1, 2, 3, 4, 5, 6, 7, 8th place, that data is missing. 1, 2, 3, 4, 5, 6, 7, 8. There it is. There's the N8. So that data is missing. Now imagine if I wanted to know if I had any missing data. Look what I could do. Let's think about this. I'm going to sum is.na my data. Here I have a function within a function. So let's go to the inner function first. The is.na. Well, the is.na is giving us back this vector you just saw of falses and trues. And now I'm going to add them up. Wait a minute. Isn't adding something you do with numeric data? Yes, but remember implicit coercion? If I need numeric data, there will be implicit coercion of these falses and trues. And what will that implicit coercion give me? What is a false turned to when it's turned to numeric? It's a 0. What is a true turned to? It's a 1. So when I sum is.na my data, it tells me how many missing data elements I have, and I have one of them. Imagine if you had a data set in which you had 1,923 people, and on one of the variables you wanted to know how much data was missing, you could use this. You could sum up for that variable the is.na. The is.na will turn anything in that variable into false or true, depending upon whether it's missing, and summing will sum up where only the trues will get a 1, everything else will get a 0, and so that you end up with that sum showing you how many missing data points you have there.